All right, good morning, everybody. Thank you for joining us this week. So today we have a guest presenting, John Devine, General Manager here at Fireye. So before we start, if I can just ask you all to keep your phones muted, and we'll actually begin. So here, we'll hand it over to John.
Well, good morning, everyone. Hope you're all doing well. Thanks for joining today. So the presentation today is going to look at the Fireye integrated scanners from our multi-burner optical flame scanner line. I'm picking the Insight scanner ranges, as you can see on the first slide, because that's a very popular product for us. There's over 150,000 of these in the field, and these have a lot of features and benefits that will provide some good background on the various applications they can cover as we get into the presentation. The slide shows the Insight one on the left. That was first introduced in 1999 actually, and Insight 2 in the center about 10 years ago, and Insight 4 is on the right about 2 years ago. And we'll focus mainly on the newer Insight 2 and Insight 4 in the presentation today. These scanners are typically used in very challenging applications where you may have a high level of reliability required, high detection required, high sensitivity, a lot of adjustment in order to detect the flame or to discriminate between flames and a background, or perhaps multiple flames. Detection may be required where you can select one target flame from a mass of other flames, for example in a power boiler. So each of these scanners has the capability basically to be set up to detect the fingerprint or the signature of a particular flame and ignore all of the other background conditions or other flames that may be present. So probably a good place to start. What is an integrated scanner? Well, basically it's a true one-piece system where the sensors, the detection, the amplification, the processing, the user interface and the interface with the outside world are all basically contained in one device. So there's a lot of advantages of this type of design over the traditional discrete type systems of the past. And in those cases the sensor was typically mounted on the burner with an expensive shielded cabling run between the sensor and the amplifier. And the amplifier may have been located in the control room of the plant or in some air-conditioned area in panels, and that would then provide the interface with the outside world in that case. Using integration, we can eliminate that special shielded cable cost. We can get rid of panels for amplifiers, and we can, we don't have the losses that used to occur between the sensor and the amplifier, as everything's directly coupled in this one-piece design. So for that reason, most of these modern flame scanners are fully integrated products. Agency approvals and certification are very important, obviously, to the customer base. These scanners carry a host of agency approvals for global deployment. They carry safety certifications, and they really are deployed across the world in power and utility, petrochem, oil and gas, marine, large industrial, and many HVAC applications. Usually, as I said, on the more challenging jobs. They're also available in a variety of different types of enclosure ratings to cover installs in potentially explosive atmospheres and different zone classifications. So IECEx and ATEX, for example, would be examples of those explosion proof requirements. So let's talk a little bit about the Insight 2 flame scanner and some of the features that it has. It's a SIL 3 certified device. That means it has a very high level of safety integrity, a lot of redundancy built in. So it's considered to be fail safe in a very high case. So typically in these applications, it's when they need the maximum safety integrity for their systems. So that's certified. It's been tested by UL, and it carries that SIL 3 certification. It means that the probability of failure on demand for this product is very, very low. The standard scanner suitable for a Zone 2 application, it's Class 1 Division 2, Groups A, B, C and D, and EXNA as a standard, and there's also a EXD version available with either a cap that goes over the end of the product or an alternate housing available, and we'll talk a little bit about those as we go through. These integrated scanners all use solid state technology, so that means the sensors are actually solid state devices. They're not like the older UV tube design where you needed a shutter to self-check them. They're inherently fail-safe, so the self-checking is done electronically inside the control. They can operate on any fuel, any type of burner, We have IR and UV available and dual cells, so we can do both. We have 2 relays, 2 form C contacts, so we could set those relays up, for example, for main flame or pilot, or we could have one from IR, one from UV, or we could have a mix of operation for the relay. So one could be UV IR, one could be UV only, etc. There's also 4 user files for different firing patterns. These are very useful because we can set up 4 completely independent setups. So we could use one for gas, one for oil, one for coal. We could use them for different conditions, maybe a startup condition, or observing a pilot or an igniter, and then switching over to a main fuel setting. So it's really very, very flexible. So you've got 2 relays and 4 files for each of the setups on this scanner. All of the integrated products are 24 volt DC. This one carries 2 outputs, 4 to 20 milliamp outputs, along with each of the relays, so that you can see a signal to the BMS or the DCS to tell you the flame signal. It carries a fault relay, so in the event you have a failure, you'll signal a fault. You have remote communications, so you can communicate with software, and we'll talk a little bit about that if we have time at the end of the display. We have a program called FEX that allows remote programming and remote monitoring. You can do the file changeover remotely, and you also have, as I said, different versions of housing. So we can do ATEX, IECEX, EXD. We have stainless housings for marine applications. So a lot of flexibility in the type of configuration that you have for the scanner. And this one has a VFD display. Some of the others have an OLED that we'll talk about. So on the display types, there are 3 available for the Insight 2. So you have the standard display, which is a vacuum fluorescent text-based display. So it actually gives you text-based information, very easy to read and understand. There's also a wireless version so that you can actually program it remotely using a wireless handheld. And there's also a blank display version, which is shown there. If you wanted to save some cost, you can actually supply the scanners with blanks, and then you can use software to communicate and set them up. Basically, on the scanners, the advantage of having the display on each unit is you can do all of the programming required to set it up from that keypad and display. So the software is an option, but you don't have to have it. You can program it from the scanner itself. A quick overview of the keypad. There's 4 keys. That's a pretty standard function for us. You can scroll through the menus. You can enter the menus and you can do programming. These scanners have an auto-tune function, so you can tune them automatically or manually as you choose. And there's really 3 typical menus. There's a status menu that shows day-to-day information. There's a programming menu that allows you to get in and set the scanner for the particular flame that you're looking at. And then there's an auto-tune menu if you want to tune it automatically. On the Insight 4 scanner, similar type of features on this product as well. Probably the key difference is this uses an OLED display. We've switched over to this type of display. It's a more modern functionality, and it actually works very well in bright sunlight as well as in dark conditions. So we find it's a lot easier to read if you're in a very sunny environment. This is also available in a multitude of housings. These have single cells, so they're either IR or UV. They don't have the dual cell option of the Insight 2. So they come with 1 relay and 1 setup, although they do have the 4 user files so that you can configure it for multiple applications and multiple firing patterns. Again, they work with remote communications. They also have remote file changeover, and we've included a function called file change on the fly, which is quite nice, which allows you to put a timed function on a file A setting and then switch over to file B automatically based on a timer. So you might do that, for example, if you had a very soft ignition flame, so you needed a very high sensitivity, and then you can change over to a main flame designation. On the Series 4, the keypad display is actually incorporated into the housing design, so it's more similar to the Insight 1 in that respect, so it's not removable. On the Insight 2, the display is separate, and you actually put it in place with a locking ring, and that's because there's several different types of displays available on the Insight 2. So you can use the wireless or the handheld or the VFD, etc. I talked a little bit about the alternate housings. These are some examples of some EXD enclosures. For the Insight 2, in the center on the lower part, you can see the cap that fits over the end of the product. That makes it a Exd configuration, and you use different glands for the cabling. Or you can go to these alternate style CX housings, we call them, and they allow you to have a bit more space, particularly if you're using a heavyweight cable. So maybe an armoured cable is coming in and you need more space for terminations. You also have a stainless steel version, which we use for marine applications. So the top housing is 316 stainless steel and also painted, so it's very good in a corrosive environment where you may have salt water present. As you can see on this slide, we've got one of the housings open and you can see the terminations. You can see there's a lot more space inside for bringing in a heavier cable, and you use a more standard type of termination versus the standard CX housing that requires the cables to be terminated behind the display. So here's a couple of comparisons on some of the products. Just a straightforward comparison. You can see the difference in the displays that I mentioned. They used typically different cables. Insight 1 would have one cable connection, as would Insight 4, whereas the Insight 2 has two cables because there's two relays, two outputs, etc. The flame relay and fault relay configurations are shown below. Generally, the scanners, if they go into a fault condition, if it's a serious fault condition, they will open the flame relay as well, but they'll signal the fault independently, so the BMS or whatever we're hooked into a PLC can pick up that fault condition. There's a few subtle differences in some of the contact ratings, although nowadays all of these are available up to 2 amps with 230 volt AC maximum on the flame relay contacts. All three scanners respond to the same wavelengths, so for IR we're running at 700 to 1700 nanometers, and UV's 296 to 320 nanometers. So they're the two ranges, and all of the scanners will use those same types of cells. We use a UV super blue on UV and a gallium arsenide chip on infrared, a photodiode. Flame detection algorithms are fairly similar, although one of the things that we've included on the Insight 2 and the Insight 4 is the ability to set a switching threshold based on the front end gain. And I'll talk about that a little bit more as we go through, but front end gain is very similar to what you would see on a camera. In a low light condition it will increase the gain automatically, and in a high brightness condition it will reduce the gain automatically. All these scanners have this automatic gain control, which we call front end gain, but on the Insight 2 and the Insight 4 we've added the ability to set a switch threshold on that, which will open and close the flame relay. That's quite an advantage if you have, for example, a tangential furnace where you have a fireball with a lot of brightness in the background. Occasionally when you turn the target off, that fireball will get brighter because there's more air going in, and you can set a switching threshold on that as the FEG, as the front end gain, responds to that increased brightness. You also have the ability to use fibre optics, so if you have an obstructed view, or perhaps you have a need to get closer to the flame because you're away some distance from the flame itself, you can use fibre optics that pass through the burner. They have an inner and outer carrier with a fibre optic bundle inside. They can be quartz or glass. Quartz is for UV, glass is for infrared. Quartz does both actually, glass is for infrared only. And these inner carrier assemblies will allow you to basically see the flame, have a better unobstructed view of the flame. Or you may have an application where they have a tilting bucket where you need the fibre optic to move, and they can be arranged to move with the bucket, so they have a very good locked-on view of the flame. That information is then transmitted down the fibre optic bundle and provided to the scanner. So the scanner's mounted outside in a cooler, safer area, and the fibre optics transmitting that flame over. These are rated for about 400 degrees C, so we have a very high temperature rating on these bundles. And again, I mentioned the SIL rating. The Insight 1 originally was a SIL 2 level, and we're now at SIL 3 for Insight 2 and Insight 4, which is a higher level of safety integrity. So just a few examples of where these scanners may be installed. On the left there is a coal-fired power plant. This is a mill group of burners. There's four burners in this mill group, so the coal's passing through these pipes and then creating the flame on the inside of the furnace. I think there's 20 burners on this unit. There's an Insight 2 scanner mounted on each one. You can just see that on the left-hand side in the centre. So there's one on each burner. They're using a fibre optic. The fibre optic passes down through a pipe. It's about 10 foot long, and then passes the flame signal, the flame information from the coal flame back to the scanner. These scanners we also use with FEX Software, so we can do the programming remotely. But again, each one has its own display, so you can program it on site as well. Sometimes it's useful to be there so you can actually see the flame as well while you're setting up. Other times it's not so important and you can do it all remotely. On the right hand side is an example of a large industrial type burner. This is a gas-fired unit. You can see the gas pipe around which is that grey pipe passing around the yellow closure plate. Usually the issue with these type of burners with all the gas canes is actually finding an area where you can place the scanner. It's quite difficult to fit the scanner in because there's a lot of obstructions and pipes and so on in the way. This is a fairly straightforward application because it's one flame as opposed to the coal-fired unit where there's multiple flames, so we have to be much better at discriminating the target burner. In this case there's one flame, so the off condition is a dark furnace, so it's fairly easy to discriminate. But typically they use a higher end scanner just because the burner is a much larger capacity, so it's passing a lot more fuel through its burning. Here's an example. These scanners are actually shown. They're Phoenix scanners. There's a couple of burners on a dual chamber boiler. This would be considered probably an HVAC type application, a power boiler. Could be in an airport or something similar to that. So here they have a scanner on each burner. There's two independent flames, and both flames contribute to the output of the boiler. Here's an example again of a twin tube unit, but here you notice they've got two scanners on each of the burners. So in some cases we're operating with redundancy. So you might have a requirement where both of these scanners have to see flame. In some cases, if it's a high safety integrity system, or it could be that either one is sufficient. So they could select it so that either one of these sees flame and they're still operating correctly. And again, here's another example: a power unit, two burners in a power unit. They're actually using again a voting system, so they've got two scanners on each burner, and I believe in this case both scanners have to see flame. One's looking at the outer ring of the burner, and one's looking at the inner ring. And that's a common configuration if you may come across a low NOx burner or an ultra low NOx burner. They may have a center portion of flame and then an outer ring of flame, and they may be required to focus on both of those to ensure that the burner is still firing correctly. Here's an application in a refinery. This would be a Class 1 Division 2 or EXNA application. This is a gas furnace, I believe, and they're using an Insight 1 just to look through and detect the flame on the gas furnace. This is a rotary kiln in a cement plant. Here they have one Insight 2 in the centre. They're looking down the burner. I believe this is a Thieves burner. It's looking down the centre, and there's a long rotary kiln behind this. You may have seen these in lime kilns or cement plants. Very long pipe where they rotate and they burn coal, pulverised coal in there. So there's one scanner in the centre looking down the centre. There's also one to the side that's looking at the side. These get incredibly hot, so they have a very, very bright flame, so they typically have a low sensitivity setting on these. This example is a paper mill. This is a startup burner in a paper mill. This is up in Canada. This is a colleague of mine, Willie Vandermeer, who's setting that up. So we're using the Insight 1 scanner in this case. It's actually looking at this startup burner, proving that flame is there. That burner will warm up the furnace, and then there's another larger burner on top, which fires down and creates the energy, the steam for the paper mill process. And I think this is the final example, but this one actually shows you two examples of Exd enclosures. So this is a sulfur recovery unit. This is asymmetric. I believe it's a company up in Canada that make these. So this unit's actually involved in it's what they call a Klaus furnace. It's involved in sulfur recovery processes in petrochemical. These typically are always Exd because there's a risk that explosive gas could be present, either permanently or intermittently. So these scanners are completely sealed from the outside world and can't generate a spark in any way to cause an explosion. They can also contain an explosion within the housing should any gas get inside. Oh, there's one more. So actually, there's a few more. So this is a big HVAC application, a mobile steam unit. So this is an application where they might use a more complex scanner just because of its size. I think these are about sort of 70,000 pounds per hour of steam. And then another application, this is a big industrial burner. This is using a fairly simple scanner. In this case, it's the UV tube based design, 65 UV5, but again, integrated design. And they're using that just to detect a single flame, which is a dark condition when it's out. So lots of different applications that use these products. So this is the theory part. So we'll talk a little bit about the theory of detection because I think it's quite valuable to understand what the scanner's looking for. So often, we talk about seeing a flame. We're looking at the visible part of the flame. So we see that characteristic blue for gas or orange for oil. Or yellow for oil, and then a sort of duller orange for coal because it's a dirtier fuel typically, and that's the visible part. That's the bit that you see with your eye. Well, the scanner's really not looking at the visible zone. The scanner's looking at ultraviolet and infrared, and you don't see that with your eye. So often the use of text-based displays or software is very valuable because you can actually present what the scanner's seeing, which you can't necessarily see with your eye in a graphical way or in a text-based way. So you can understand and relate to what the scanner's picking up. Now, if you look at these various fuels, all of the fuels contain UV and visible and infrared in different measures. And these are what we call the spectral frequencies of the scanner. Spectral wavelength is probably a better term. So when you hear people talking about wavelength in nanometers, that's the spectral wavelength. It's the way that the waves of light respond and the zones that the waves of light are in. And that's different to flicker frequency, which we'll talk about a little bit later. It's often confused, but flicker frequency is a different thing. So here we're looking at the spectral wavelength of the energy of the light. So in the basic cases, all flames contain UV and IR. As I said, in the first third, you typically get the highest UV radiation and the lowest infrared. And as you get further out in the flame, as the flame propagates out further into the boiler, you tend to get a lazier flame with higher infrared radiation and lower UV radiation. So the first third is what we typically refer to as the primary combustion zone. Now that we're into low NOx and ultra low NOx burners, they are performing slightly differently because they tend to have a much slower mixing. So they have fuel staging and air staging perhaps, so the mixing's done over a much longer period. But the typical design for burners would have this primary combustion zone where all of the intense mixing goes on just in front of the bluff body or the diffuser. And that's where you get a lot of UV generated because of that mix. Now, when I say a lot, that's a relative term because UV is actually the least available in terms of energy. It's only about 1% of the available energy, but it's a very important 1% because it's only found in a flame. Particularly when we're also looking at things like the flickering of the flame. So we can detect the UV in that first third of the flame. Even though it's a small amount, we have very high sensitivity on the scanners in order to detect that successfully and reliably. The visible light, the bit that I mentioned that you see with your eye, that's 9% of the flame, and infrared is the last 2/3. It's about 90% of the energy of the flame. So there's a lot of infrared out there. So we ultimately like to look in that first third because that gives us a nice blend of the different spectral light. So here is an example. This is our ideal mounting position. It's one that we never get. Unfortunately, we tend to always be struggling to get this really good line, cross-sectional line of sight across that first third and out beyond that. Typically we're considered at the end, so the burner manufacturer makes the burner and then they put the scanner on in a suitable position where it's convenient to fit it, and we may be looking directly across from the burner closure plate directly across the side of the flame, potentially not in that first 1/3. So, but this would be a perfect line of sight where you would have very good detection and be able to discriminate very well, because you're looking at those high frequencies, high signal in that first third, and you can ignore the background condition very, very well. So we have on our scanners, we have a thing called flame quality, and that's quite useful because it provides you, when you set the scanner up, you can look at that flame quality and see if it's varying from day to day or if it's still at a good level. It's typically capped at 100, so it's a 0 to 100 scale, and any of the signal above 100 is considered 100. So it's very stable and it doesn't fluctuate a lot, because a lot of the customers that we hook into on their BMSs don't want to see the signal jumping around, because that concerns them. So the actual raw value signal can go from 0 to 999, so almost 1,000 for each of the cells. But anything above 100 will give you that 100% flame quality. So typically you might be running at 500 on your raw signal, so you're going to get a very nice stable 100 flame quality, get a very nice stable signal into the BMS, and they'll be satisfied and happy. Now there's a number of UV and IR frequencies that the scanner can choose from when it's carrying out its learn on. And I'm going to talk about them a little bit more and explain what they are. That's the difference between flicker frequency and spectral wavelength. So we'll talk about that a little bit, but these will automatically detect those. It will scroll through those frequencies and pick the best point of discrimination between flame on and flame off. So when you're learning a flame, if you're doing the auto tune on the scanner, typically what's going to happen is you're going to set the burner to the lowest firing rate. You're going to learn that as flame on, and that's with the target burner at its lowest firing rate and all of the other background running. You're going to learn that as the flame on condition, the worst condition if you like, and then you're going to learn the flame off condition when the target burner's off and all of the background is on. So you're going to use the scanner to pick up a differential between the target burner, in what it sees in the target burner, in the signature or the fingerprint of the target burner, versus what is available in the background. And that's where that auto tune comes in. So I mentioned front end gain. Front end gain is important because these scanners will use this front end gain to compensate for minor variations in the flame. So once you've set the thing up and you've determined the settings that it needs, it's going to compensate for minor changes in flame. So you may have a situation where the fuel is damper and you've got a slightly duller flame than you had the day before, and the automatic gain will compensate for that and try to lock on the signal based on what you asked it to do when you set it up. It's also directly related to the aim number. So when you're doing your initial setup, typically what you do, you put the scanner on and you'll look at the aim that it has on the flame, and it will actually tell you via the aim number what it's seeing, and you can use swivel mounts or you can adjust the position of the scanner to give you the optimum aim during setup. The learned FEG, what you learned at the time, you can use that as a reference point. So you can say, look, when I learnt this thing, the flame, the FEG, the front end gain number was 100 perhaps, and you can store that and say that's the reference number during the learn process, or you can do it during the auto tune. And it will constantly compare the current front end gain against the learned value, and it will make some adjustments based on that as well. Okay. So let's talk a little bit about discrimination. So discrimination is required if you're in a multi-burner furnace where you may have multiple flames, or if you're in a furnace where it may have a very bright background and you want to make sure that you successfully detect the flame off. So discrimination is basically differentiating between the target burner and the background condition. So what will happen is we'll typically pull a graph. These examples are shown from the software, but you can also do it on the display using the numbers that are shown on the display. And we can look at the signal, the amplitude. Amplitude is also termed as brightness or nearness or intensity. The power of the flame, the magnitude of the flame, they're all basically giving you the same information, the same signal information to the scanner. Now that amplitude, that signal of the flame varies over time. Now if you imagine if you're in your house and you're looking at a coal fire and you're looking at the flame, it's not constant, it's flickering, it's moving around, and that's the signal changing over time. Now what we can do is capture that signal changing over time and convert it into frequencies. So when you look at these graphs, it sort of shows it very graphically. You can see the amplitude on the left axis, and the horizontal axis is showing the flicker frequency bands. So we can actually measure the signal that we're seeing from the flame, the amplitude of the flame throughout all of these different flicker frequency bands. And when we find a band where there's a very good differentiation between the signal for the burner on and the burner off, even if the background's present during the off condition, we can select that flicker frequency band and then only look at that band going forward. So we can select a very fine band, maybe 6 Hertz wide, 3 Hertz either side of the center point. And if we know that the signal has a lot of differentiation, a lot of discrimination between on and off conditions during that flicker frequency band, we can utilize that going forward and know that that's always going to be the case. And here's a little bit more information trying to help lay that out graphically. So if you look at that top trace, that's a real-time trace from a target flame on a power boiler. So basically what we see, we measure a number of dots across that trace, and those dots represent the signal, the amplitude that we're seeing across all of the flame flicker frequency rates. And then we tie that together, we create a graph out of it by drawing a best fit line between those dots. So if you look at this example, we've taken a real-time trace from the target flame, which is the black trace, and the red trace is the trace we've stored from the background condition. So that's with the other flames on and the target burner off. So then you scroll along the flame flicker frequency bands and you pick a point where there's a wide differentiation between the target flame trace and the background trace. And in this case, we're looking at maybe 123 Hertz, somewhere between the 117 and the 140 Hertz range. And you can see in that case, we've got amplitude of 40 when it's background only and 60 when the target burner is on. And that's a good differentiation between the two. So it gives us a very repeatable on and off signal when our target burner starts and stops. Now, if you look at the around the sort of 15 Hertz or even the 47 Hertz line, you can see that the real-time trace is much closer than to the trace from the background flame. So you wouldn't select that flicker frequency because they're very close together. So you wouldn't have a differentiation between on and off. So this is basically the process of discriminating the target burner from the background. So some of the terminology. So it's worth explaining this. We throw these words out a lot because it makes us sound like we have a lot of expertise in this area, but they're really not that complicated. You may hear the term FFT, fast Fourier transformation. That's often referred to when you show that graph, for example. It's a fast Fourier transformation graph. Basically, it's a mathematical algorithm that allows us to take the average amplitude over time, so that sort of adjustment of signal, that flickering if you like, but the adjustment of signal, the modulation of that signal over time, we run a mathematical algorithm over it and we convert that into flicker frequency bands. So we go from a time domain where a signal is changing over time into a flicker frequency domain. And we can use that to separate things up so that we can look at particular flicker frequencies and isolate them from the background. Amplitude, again, it's the signal seen at the scanner detection cell. It's derived, it's power, nearness, brightness, intensity, magnitude, signal. They all basically mean the same thing. So that gives us a signal onto our cell on the scanner, and we read that as a value, and the raw value is 0 to 999. Flicker frequency. This is the frequency of the flame flicker that we calculate through that fast Fourier transformation algorithm. Flicker frequency, not to be confused with wavelength, light wavelength, two completely different things. So the flicker frequency we're looking at is the frequency of the changing signal over time converted into a frequency band. Another one, FEG, I've talked about, front end gain, also referred sometimes as AGC, automatic gain control. That basically is just something that allows the scanner to adjust, increase or decrease its amplification based on the light that it sees, or the signal that it sees, I should say, from the flame. This is also going on in the background, and it's independent of any user gain adjustment in the scanner setup menu. So this is automatic, it happens in the background, and it's designed to maintain the scanner at a good signal level close to what you set it up at on the first day. So it helps you take out variations in signal, minor variations in signal from the flame that could be changing over time. FQ is the flame quality number. We refer to this is the 0 to 100 scale I talked about. It represents how close the measured value is on the target flame to the one that you selected at setup. It also determines the on and off thresholds. So typically if you've got 100 flame quality, we might have 20 as our off threshold and 40 as our on threshold for the flame relay. So as long as you're at 100, no problem, flame relay's on. If you drop below 20, your flame relay will open and signal that the flame's gone off, and you'll have to go above 40 for it to come back on. So you get some hysteresis in the operation as well. And in comms address, that's pretty straightforward. These scanners have a multi-drop communication capability. So if you're using a multi-drop, you may need a unique scanner address for each of the scanners. You can typically handle 32 scanners on one comm address, but I've actually seen up to 96 handled on one loop without too many problems. But obviously the more information you capture, the more information has to be transmitted on one multi-drop line. It's possible to hook these up using USB ports to have a laptop or a computer in a control room running several loops of scanners. What to do if the aim's too high? So one of the problems you can come across is when you're aiming the scanner, you have a particular flame that you're looking at. You're looking at the aim number first to see if you're getting a good sighting of the flame. Sometimes you can have an aim that's too high. Now we have the ability to adjust the range of the scanner. Typically there might be 3 or 5, or in some cases on the newer products 10 adjustments, which should more than take care of adjusting the aim number. And you're looking for an aim number that's not too high, not too low. You're looking for something in the middle. So 15 to 20 is a good aim number. 60, if you go over 60, you could saturate the cell, so you would switch the range down. If you're very, very low, you would switch the range up. And you've basically got high, medium, low settings, or you've got this 1 to 10 setting on Insight 4, which allows you to make that range adjustment during the setup. Occasionally you might come across a fuel that's incredibly bright, and even though you've set the range to the minimum, you can still have a value that's too high and saturated. So one example that comes to mind was a gas oxy burner where they're using oxygen instead of air. It's a very, very bright flame, and even though you've got the scanner set to the minimum to low on the ranges, you're still getting a signal over 60 on the aim. So the simple thing to do then is to try to adjust the sighting so that you're not getting such a good view of that very intense light from the flame. Or you can actually orifice it. You can use orifices which will reduce the amount of light going into the scanner. These are a series of discs with holes at different sizes, and you can actually work your way down and reduce the light and the signal that's going into the scanner. Or in this case, we've shown a valve. I mean, you can simply close a valve to test that theory as well, to reduce the amount of transmission into the scanner. So safety first. This is this is probably the most important slide in the whole presentation. After you've commissioned a scanner and you've set it up and you think you've set it up correctly so it detects the target flame, you must turn off the target flame to make sure that it does detect that the target flame's off, that it's still not picking up the background. So this could be done by closing the fuel valve, ensuring that the scanner relay opens and it doesn't detect the background. And the reason that this is important is the whole purpose of this scanner is that it's going to detect the target flame only. It's going to see it when it's on, and it's not going to see it when it's off. So if you do pick up the background, that sort of defeats the whole objective of the safety function of the scanner. That is the safety function. That flame relay is the safety device that's integrated with the user's BMS or PLC system. So very, very important. Sometimes very, very difficult. Some customers may be in a process. Sulfur recovery comes to mind. They really don't want to turn the burner off when you're running it. Once they've got it on, they don't want to turn it off. But it's very important to do this and to try to convince them to do at least one time to make sure that's working okay. And actually, I just got a question from Chuck. Thanks, Chuck. Could the sight tube penetrate into the burner to look at a specific target? It can. I mean, typically, if the sight tube goes into the burner, it might be subject to heat. So there might be some concerns from heat, but I mean, sight tubes may protrude in past the closure plate and be behind refractory, for example. Often, if you need to get closer to the flame, we recommend using fibre optics. So, for example, if the scanner, if you can't see the flame, the visible light of the flame, the scanner's probably not going to see the UV or the infrared. So, if you put the scanner on, you have a very, very low aim number. And no matter how you adjust it, you still have a very low aim number, even though it's set to maximum. It's highly likely that you may need to change the position, the viewing position, or you may need to use fibre optics to get closer to the flame. The advantage of the fibre optics is they can go up to 400 degrees C. Well, they can go up to probably much more than that because they have cooling air as well. So sometimes it's 1,000, 1,200 degrees C outside the fibre optic itself. Some projects that we've worked on to give you some idea of the type of applications where these are used. I talked about marine applications. The Shell Prelude is a floating LNG plant. This is moored off the coast of Australia. It's the largest floating object in the world, I believe, or certainly was at the time, 600,000 tonnes. This has, I think, about 60 scanners on board, all stainless steel, explosion-proof Insight 2s. And this unit has been sort of on and off into production. So, but they basically, this would be considered a very intense marine application where there's a lot of saltwater corrosion to worry about. And another example of these floating platforms. This is a Japanese company, Impex Oil, through Alfa Laval, again in Australia. We sold these through Alberg, stainless steel Insight 2 scanners, again because of the marine requirements. We do a lot of power plants. We do a lot of US power plants. We do a lot of power plants overseas. This one is Jeddah South. This was done through Hyundai Heavy Industries, HHI, you may have heard, in Korea, and again Insight scanners. I think these are Insight 1 scanners if I remember rightly. Abu Qir is another thermal power plant. This one's in Egypt. These were sold through Ansaldo. Insight 2 scanners. This one was quite interesting because we actually lost this project to a competitor and then they struggled to discriminate. So discrimination between target burners and backgrounds is not easy. It's a very difficult and challenging environment for these scanners to perform. So we actually got back in there. We provided some samples to them to test. They were able to get it to work successfully. So we then replaced the products in the field, and I think we've got several more of these boilers as we've gone through. The picture in the centre, actually, interestingly, that was from the plane on the way over there, and it really is a desert out there. So as you can see, so we do a lot of refineries. We work with the big petrochem oil and gas burner companies. Johns Inc., Zeco, Calidus. There's several others as well, but they're some of the bigger ones. So we provide scanners to them. We do a lot of work in Russia in refineries. We do a lot of work at Marathon Oil and Exxon and Shell and all the big oil companies as well. Fort McMurray, that was a great environment for us for a long period of time. It's suffered a little bit since the oil price crash in 2016, but at one time there were literally thousands of scanners going into this huge development. It was like a city, just like a city. They're actually pulling the oil out of the sand, so they use a lot of steam. They either bring some of the sand into these big vehicles and they pump steam in to retrieve the oil, or they pump it into the ground and bring the oil up. So it's a very interesting project as well. Another Russian one, Insight Flame Scanners. One of the interesting things for both Russia and Canada is we have a very wide temperature range. The standard is -40 to +65 on these integrated scanners, but we actually have cold start tests down to below -50. In some cases we've even done them down to -60. So these can go in very, very harsh outdoor, very cold environments. So they're very rugged devices as well. So there's some applications. So we still got a little bit of time, so I think I'll go through the Fireye Explorer software. So as I mentioned, all of these scanners can be hooked up to a software that we supply called FEX, Fireye Explorer. This is a really nice package because what it can do is allow you to connect a large number of scanners and look at all of the information from the scanners graphically. Now, why is that important? Well, you can't see what the scanner sees with your eyes, so you really need a representative way to see what the scanner's seeing in order to set it up. Now, you can do that from the keypad. You can do, you can do that remotely. We can do a remote keypad as shown here on the software, or you can do it through the software itself, where there's a lot more capability and ways to present the information in a graphical format. So we can hook up a number of these scanners to this software. We can configure these graphics from graphics that are already available. We can pull them down. We can set them up. We can program the scanners remotely. We can see the information. We can log. We can trend. We can do historical. It's a very neat package for getting the information out. So it's for use with Insight 2 and 4. It's a PC-based Windows software. It's good with the latest versions. I think Windows 10, we've got a version for that as well. You can remotely operate the scanner keypad, as you saw in that picture. You can remotely monitor multiple scanners side by side if you wanted to look at them side by side. But you can observe a lot of the stored information. You can store information from logging. You can see flame signal graphs, scanner bar graphs, etc. So it's a very, very valuable tool for setting up. There's also a very nice package in there called a tuning bay, where you can actually go in and you can do all of the settings required for the scanners from one page, which is very, very useful. You don't have to scroll through menus in that case. So here's some of the things it can do for you. First of all, a very important one, you can upload, download, so you can actually store all of the programming information from the scanner as a file, so that you've got it, you can put it on a zip drive, you've got it stored, and it works very, very well for the customer to store all of his files. If you have an issue and you need to move a scanner around, change a scanner, you can just dump that file back down into the scanner and you're up and running. You can store furnace layout information. You can set the scanners up similar to the configuration of the boiler. You can do the trending, and I'll talk a little bit and show you some examples of what you can do on the trending as well, which were very helpful in a recent application that I've worked on. But you can look at the historical data, you can look real time and so on. So it's very, very helpful. And we've got a question from Reggie. Thanks, Reggie. How does the laptop connect to the scanner? Well, it's a multi-drop configuration. You have a RS485 loop. The scanners operate on Modbus, so it's a sort of from scanner to scanner to scanner, then to a RS485 to 232 converter, and then into the laptop. So it's pretty straightforward. You need one RS485 to 232 converter for a loop of, we recommend about 32 scanners on a loop. Usually a PC has multiple USB ports, so if you had more than 32, you could do a second loop, or you could run with more on that one loop. But that would slow down the information, obviously. One of the other things that's important is a lot of people will say, well, can't I just pull the information directly from the scanner without using the software? Well, it's possible to do that, but if you imagine how much information we're pulling over on our FEX software, on the Fireye Explorer software, it would make it very, very difficult to write a program to do that when everything is done for you here. So these graphs, if you imagine the amount of data that's required to provide these graphical depictions, there could be hundreds and thousands of data points that you're bringing in, so it's very difficult for you to write that from scratch. It's very long, it's long-winded and a lot of effort. So one of the things we do have on this is we have the ability to use the PC as a node on the customer's system. So for example, the PC becomes a node on his distributed control system, and he can pull information from the PC into his DCS or PLC system. And that's an open protocol, an OPC type network. So that's quite useful, because typically the customer may not want to see all of this information. He may just want 10 things. He might want to see the flame signal, the flame relay status. Maybe look at several bits of information from the scanner, the raw signal value, etc. He might not want all of it, whereas everything's available on FEX already pre-configured. All of the libraries, all of the way that you present the information is all there for you, and it's done. And it's a very low cost package. So it sort of makes sense to use that because it's all pre-configured. These flame status faceplates are examples of what's there available in the library. So you can bring information out, you can present it. This shows a depiction of a different type of scanner where you can look at temperature information as well. But basically you can bring all of the criteria from the scanner and present it as a faceplate. Now, for those guys who've been around in the business for a while, like myself, you can actually remember this looks very frighteningly familiar to the old amplifier, the old card-style amplifiers that we used to use. So we're sort of going back in time a little bit. In the past, we had these discrete scanners, scanner, cable, amplifier. Now we've got the integrated scanner, so we don't need the remote amplifier. So what we're trying to do is create that on software so that you can look at it in the same way. So we sort of come round in a full circle to some extent, although these are all software based. So I mentioned the tuning bay. This is fabulous. I mean, this is a really nice piece of software, and it allows you to go into the scanners. You can set this up as an array of different scanners as well, so you can set multiple scanners up at once, but you basically have everything you need to set that scanner up on one sort of tuning bay. So it's really useful. You can make changes on the fly. You can see the response immediately as soon as you send the signal down. You can look at the gains, you can look at the settings, you can look at the signal, you can look at everything. So you can go in and you can change, so I want to change the frequency band up one value. I can instantly see the response. It's very, very useful for setting up the scanner and for, as it says there, for making very educated decisions about what you should change or what you should leave as it is. So I like this a lot. This is a really nice tool for setting the scanners. Generally speaking, you may not need it on a simpler application where you have maybe one flame in a chamber, but when you're on a power plant that may have gas ignition, oil igniters, coal fired, it may have gas fired as well. It might have heavy fuel oil running in some cases. There may be multiple conditions, and this allows you to really review all of those conditions and make sure that the scanner works through the whole lot of them with a good setting and good reliability. So some examples of customer screens. You can actually customize these to look at what you want to look at. You can look at graphs, you can look at trending, you can look at the FFT curves. In the bottom right, you can see in that example, we're looking at information from the scanner that looks at the signal versus the flicker frequencies. You can look at it as bar graphs, or you can look at it as the display. But the nice thing is you can do it all in the comfort of the air-conditioned control room, rather than having to walk around the power plant up and down the decks to review it on the scanner itself. Another example, this is a customer where he's just set this up so he can look at the things he wants. He's using the tuning bay, so he's actually making some adjustments, and he's looking at the tuning bay while he does it, and he's also looking at the response of the FFT graph, so he can see the signal change over time at the various flicker frequencies. One of the things that we're experimenting with as well using this software is called burner balancing. One of the issues you get in a fuel... sorry, we've got another question from Chuck. Can this data be integrated into the DCS? Yes, it can, Chuck. You can use this OPC network is probably the best way to do it. Then the computer that you're running the FEX software on, the PC you're running FEX, becomes a node on their network, and they can interrogate the PC and pull that information out. We've had some people do that through Ethernet as well. Actually experiment with that and taking data out as well. So it's possible to pull the information you need for the DCS. typically they're looking for something fairly specific, maybe certain values, not everything, so they can just pull what they need. So this burner balancing, this basically, if you look at this example, there's 6 burners in a mill group. It's a coal-fired power plant, let's say. So each one of these nodes across A, B, C, D, E, and F is representative of that burner on that mill group. So we can look at things like flame signal, UV and IR strength, UV and IR stability. We can use flicker frequency to detect the stability of the flame. So we can look for variation in the flickering of the flame to see how stable it is. We can look at the amplitude to detect the intensity of the flame, the strength of the flame. And once we've set these up, we can record these values on these nodes. Here you've got an example of 6 burners above 6 burners. We store these values and then we compare these values over time to look for changes. So if we see one that is moving out of whack with the others, we can detect that very easily, and we can use that to balance the burners. This is a problem inherent to coal-fired systems because the coal distribution, or the air distribution even, is often not exact. As the coal starts to block up the coal dust starts to block up the ducts, you can lose distribution to the outer burners, and this is a very easy way to detect this. And this is something that we're experimenting on because they're buying these very expensive flame scanners as a safety device. And as you can see from this software, there's a hell of a lot of information available that they can use for, above and beyond just safety. So again, I sort of covered that, but you can set these up to look at a number of criteria for balancing. You can even present it in different ways. So some customers prefer to have sort of dials and gauges, so they can say in the green zone it's good, if it moves to yellow it's moving out of whack, and if it goes to red it needs attention. We don't correct the problem, but we just flag it to the power plant, to the DCS, to tell them that their burner's out of whack. You can look at FFT charts. As I mentioned, you can look at your signal over frequency. You can compare the red is now, the green was what you stored. You can look for changes, that kind of thing. And graphing trending is very, very valuable as well. So here's an example where we use this trending. We left the unit running overnight. We were having a lot of problems with a very low signal, so we had to have a very high front end gain. So it was up around the 250, which is maximum. It was bouncing around at a very high level. You can see that in the top left corner of the trend, that green trend. And what was happening was we were losing signal, and you can see in the black bars, the black trace, the flame relay tripping occasionally. So what we did, we made some adjustments to the air distribution on the burners, and you can see the front end gain came right down into a more reasonable area, about 60. And we played around with that for a little while, and we found it was very, very stable, and we no longer had any trips. So we left this running for 24 hours, and you can actually zoom in on this so you can see it minute by minute. It's really very, very good to look for changes. And then as we went along, you can see in the sort of center, you can see that signal working very, very well, no more trips. And then they put the air back, and you can see it slowly climb back up to a very low signal again, up to 250, and we start seeing the trips again. So very, very useful as a diagnostic tool to see what's going on the flame. And here's another example. Great signal, front end gain really, really stable at 30, no trips at all. Then they do their air adjustment, and you can see we're tripping all over the place because the flame's gone away from the view of the scanner, so the automatic gains climb to maximum. You can also, I mentioned this OPC, bringing the information into another device. You can see all of the tags that are available. There's a database there. Shows you every bit of information that's logged as a Modbus value or the Modbus address, and they can come in and say pull a particular value. They may want to take 10 values from each scanner, or maybe one value from each scanner. They can just go in and select what they want. And I think that's about it. I think I'm pretty much on time.
All right, thanks everyone for joining us, and I'll send out a link to this presentation so you can watch it on YouTube if you want to review it, or to forward it to colleagues. And thanks again for joining.
Thanks very much, everyone. Appreciate your time.